Hello, everybody. First of all, thank you very much for joining the presentation. My name is Aleksandar Grbic. I'm the Global Data Center Segment Manager for the ABB, Electrification Smart Power Division. So before we start with the presentation, maybe just a couple of words about the ABB in case you don't know. We are the electric distribution company. So when it comes to the data center segment, we are dealing with the electrification of data centers from the grid to the servers, basically. And today, actually, we are going to have a bit technical discussion about the protection strategy for the highest availability. So let me share with you the agenda of today's presentation. So we are going to start speaking about just a bit about the market trends, but I think you are well aware about those. And then we are going to share a couple of words about the importance of the continuous operation, which, by the way, still remains the #1 priority for data centers. Then we are going to jump into the system design first and see where we still have the opportunity to improve the reliability and availability of the data center. We are also going to dig deeper inside of the electric installation and look how we can improve the reliability based on the components and how we selected the devices, and maybe if we could leverage also on the digital technologies, for example, to further improve the availability of the data center. So let's start our journey. I think all of you know very well those figures and that the data center segment remains #1, I would say, one of the highest growing segments. For me, the simplest thing is to explain all of us have in our pockets cell phones, right? And just think about how much data we share or consume daily. For all this data, we need data centers, right? So that's why we may expect also in the future that the data center segment is only about to grow. And yes, we speak about the sustainability of the data centers, of the energy efficiency. This is, of course, very important and key topics. Today, I want to come back a bit about still the topic that is, I would say, the #1 priority, and it's the reliability and the redundancy of data centers. Why this is, if you look at the graph on the right side, so here you can see that the cost of the data center outage still increases. This is based on the study conducted by the Uptime Institute, based on around 420 data centers, where they reported the average cost of the outage. So, and then the other graph on the left reports why this happened. And as you can see, the power still is the #1 reason for the data center outages. So could we improve this part? Could we implement something to have more reliability on the power side? So let's deep dive into this topic and the electric distribution of the data centers. As I said, we are going to start from the systems, and I think those of you who had a chance to design a data center know very well about different systems. So the first system, I would say, is the most typical one, system plus system. The idea is to have the full redundancy. So all the components that I have, I duplicate basically, so that in case that I have a fault on one device, I have the other device which will take over, or even a portion of the system. Then, if I have a larger data center and a bit more flexibility in designing it, I can go with a share redundant system, so I can multiply those, as we call them, system blocks, and then share the load between them, but still have enough power if one of the systems fail, that the other two can fully supply the load. We use the term utilization rate. So the utilization rate in this case would be 50%, because 50% of the power would come from the system 1 and 50% from the system 2. In this case, I would improve this. This would be the 3n/2, so I would have 66.7, right, utilization rate. The another strategy is the block redundant, using the static transfer switches, but again, we are here speaking about the systems. This would be n+1 redundancy on a system level. What I want to share with you, I want to deep dive more into design of this system, so of a block, and then you can design any different system you would like, so the overall data center architecture. So let's see which kind of improvements we can bring to those system blocks. The typical design of the system block looks like this. So I have, of course, a UPS, which is there in case that I lose the utility to cover the loads before my generator kicks in. So this would be the most typical architecture of a system block of a data center. I want here to underline one point. Selectivity in this kind of networks is a very important topic, and today we are going to dedicate most of the time during today's presentation on discussion on the selectivity inside of this block, because, as I mentioned, there is space for the improvement here. So why this is important? On the left side, you see the system which doesn't have the selectivity. So in case that I have a fault downstream the UPS on one of the branches, one of my protection devices upstream will trip, maybe, and I will mention afterwards, the fuse inside of the UPS or even the upstream breakers. And instead of losing just one branch, just one supply, typically in data center this would be for the group of racks or maybe for one rack, depends where downstream in distribution fault is, I would lose the whole line. I would lose the whole system block. In case that I do have selectivity, and you see over here, I would lose just this one small branch, and I would have the whole rest of the system redundant and still available. So here is actually where we need to study and to understand how we can have the full selectivity and again improve the reliability of the data center. So first, before starting on the selectivity between the UPSs and the breakers, which is, by the way, more challenging task, let me share with you some strategies for the selectivity in the main distribution boards between the breakers typically, or also the fuses, but I would say, especially in the Benelux region, that the breakers are the devices which are being typically used. So the typical strategy for the selectivity is that I select the components based on the let-through energy, right? And so that based on the component selection, I have the selectivity between the downstream and upstream device. But sometimes I cannot do this because of many reasons. Maybe I need to install all air circuit breakers, all the breakers of the same size in the main switch gear, so I cannot realize based on the selection of the device selectivity. So I need to go to different strategies, what we call enhanced and advanced selectivity, and I need to use the digital-based selectivity, communication between the protection devices, in order to send the signals to identify where is the fault and which device should trip. Maybe I didn't mention what is the main reason or main strategy of the selectivity. I want to minimize as much as possible the part of the system which is influenced by fault. So I want to have the isolation of the smallest portion of the system where the fault is. So for me, it's easier to clear the fault. And of course, I have much less impact on the installation. So for example, I can use also in the low voltage systems, and this is very interesting, the communication protocol called ISC 61850, which is, by the way, very common for the medium voltage systems, and which is basically taken from the medium voltage and implemented on the low voltage devices. So I'm further flexible to create even selectivity with the medium voltage devices. But let me jump into a more interesting topic, which is selectivity with the UPSs. Before jumping there, I want to just share with you the operation mode of the UPS. So typically UPS has 3 operation modes. One is in the normal operating conditions, when I have the generator or utility available, so I'm operating on the rectifier and inverter, right? So this is the normal operating condition. Now, in case that I do not have the generator and utility, I'm going to switch to the batteries. And I'm going to supply from the batteries through inverter the critical loads. And for me, for selectivity analysis, actually the second operation mode is most interesting. And this is when I work on the static bypass, which is inside of the UPS. Why I'm working on this device? It's because here we have thyristors, while in the rectifier and inverter we have IGBTs. IGBTs are much more sensitive components, are much more sensitive to high currents, or better said, to higher energy, while thyristors can handle higher energy or higher currents for a longer time. For that reason, whenever I have a fault or any abnormal condition downstream of the UPS, my UPS automatically switches to the static bypass. And inside of this static bypass, there is internal fuse, which is protecting it against those faults. And of course, if the fault is too high or it's there for the too long time. So let's analyze if I have a failure downstream of the UPS. So in case of a standalone UPSs, which is, by the way, an easier thing to handle, I would have the fault downstream of the UPS. My fault current would run through the circuit breaker, which is downstream and it's external to the UPS, so it's not inside of the UPS design, through the static bypass and through the fuse. This is very important, through the internal fuse, which is protecting the bypass, and then through the bypass breaker. So I need to analyze selectivity basically between those 3 devices. And then the rest of the selectivity I can do in more traditional ways or using the software tools that are used for the analyzing the selectivity between the breakers. Let's analyze more complex systems. So in case of modular UPSs, the true modular UPS each module has a static bypass inside. So it means that I also have, for each static bypass, I have a fuse which is protecting this bypass. So it means that I actually have 3 fuses in parallel. So in case that I have a fault, I do not have anymore just one current flowing through the UPS. I actually have a current which flows through each static bypass and thus through each fuse inside of the bypass. What does it mean? It means that I need to consider the fuses in parallel. And I need to consider that, of course, in a real world, there are no equal fuses or equal devices. So I won't have the equal current flowing through each of 3 fuses. So I need to take also in consideration the multiple fuses in parallel. So how can I do the selectivity in this case? One option is calculation-based. And many of you would tell me, don't worry, we have the software tools which we are using for the selectivity, but actually currently there are no software tools which are properly taking into consideration the fuses inside of the UPS. So software tools are considering the UPS as a black box, including also ABB software tool, I can tell. So this can be very challenging task. So you need, first of all, to know the data about the devices, about the UPSs. And you can, of course, have quite limiting results as you need to take into consideration those parallelization of the fuses. And of course, it's a time-consuming task. Other option is to do the test. So you need, of course, a laboratory, the certified laboratory, where you can conduct this kind of tests. You can obtain better results, of course. You can have maybe higher breakers selected downstream of the UPS. And of course, there are many combinations, and this requires investment. So this is, I would say, a better solution, but of course, it's a bit more challenging. So as ABB, we are actually, together with our breakers and our UPSs, we did this calculation for you. So we provide very simple currently tables, so not yet software tools, where you can see which breaker to select upstream and downstream based on the UPS you selected. As sometimes this is even challenging, we also are doing tests in our testing facilities to ensure that there is a proper coordination between the downstream and upstream breakers, so you can even select higher breakers downstream, so you have less constraints when designing a data center. So this would be the first part of the presentation where we share the selectivity. And now I want to deep dive more on the component base. So one option is to improve this system. The other, not option actually, one opportunity is to improve the system. The other opportunity is to properly choose and design also components. In heart of the data center, I would say lies the UPS. As we said, UPS is there to protect my loads if I have any abnormal condition or a failure or anything else. So I also should build a redundant UPS, so I can also have N+1 architecture inside of the UPS, but I want to have a real one. So I don't want to have a UPS which might have a single point of failure, which would jeopardize the operation of the whole UPS. So I need to think about every single part of the UPS. We were speaking about the bypass, so I don't want that my bypass is a single point of failure. I want to think about the communication between the devices and not to have maybe a master which would control. So all the modules of the UPS should be capable to be a master or take over, right, the whole logic. Good idea is also to have, for example, hot swappable UPSs. So in case that I need to do the maintenance on one of the modules, still I can keep running all the other modules to have the real N+1 redundancy. So typically we start thinking about the components from the UPS side and to select the proper UPS for the reliability. Next step is, we were mentioning digitalization. So we know data centers are, let's say, allowing us new technologies like cloud computing, big data, Internet of Things, data analytics, right, machine learning, and so on. But are we using those for the infrastructures of data centers? Are we using those technologies maybe also to answer to the reliability requirements? This could be also next step, or also currently there are some features we can benefit on. So for example, by continuously monitoring data center infrastructure, we can see what is the condition of each and every device. So I need to have devices which are, first of all, capable to measure, to monitor, to communicate. That's fundamental. And then I should have a system which is able to analyze properly this data. Because one device can, for example, even our circuit breaker produces a huge amount of information. The environmental parameters like humidity, temperature, vibration, corrosion, and many other, plus the number of operation, the average current, if there was a fault current interruption and what was the fault current, contact wear, right? And many other. So based on that, it's quite difficult to understand what is the health condition. But for example, if I'm using the predictive algorithms, or if I'm, again, leveraging on this artificial intelligence and machine learning, I can really analyze properly all this data and turn this data into information. And I need to turn it into valuable information. So for example, based on this algorithm and the data coming from the devices, I can give a too simple information to the data center operator. What is the current health condition of my device? And when do I need to do the next maintenance? I would say the first information is most important because I can really understand the reliability of my infrastructure and I can predict if there is a failure to happen, and I can prevent it. The other one on the maintenance also can save me some cost, right? So, okay, here you maybe don't see very well, but actually for the clean environments such as data center and for circuit breakers, for example, we can save even up to 36% on the maintenance cost because we are not doing the maintenance periodically, preventive maintenance, but we are doing it predictively, only when it's needed, only when my device is telling me I'm not in a good condition, I need to be maintained. So together with this, I would like to also conclude the presentation. So I think, digital technologies are really the future, and with this we can even further improve the reliability of the data center. So just to remind you, we were speaking about how important it is to have the reliability and the redundancy on the data centers. Then we said, okay, one opportunity is to improve the systems. First of all, we need to design reliable system, but let's look also in the blocks that we are designing. And one opportunity is to have the proper selectivity, right? And keep in mind the UPSs and design in the right way the selectivity between the UPS and the breakers downstream and upstream. Then we said we also need to think about the components in the electric distribution. So we need to have the reliable and redundant components that we are selecting, but also maybe we can leverage on digital technologies. So we can do these predictive algorithms. We can, currently we are at the stage that we are able to deep dive in each and every component, so to see what is the health status of my breaker, of my UPS, of my transfer switch or other critical devices. But why we should stop there? Let's maybe analyze also a system as a whole. Let's think about maybe interconnecting and letting also those devices communicate between them. And then we can even further go with this idea. So this is maybe something that could happen in the future. So we can monitor the infrastructure of the data center, right? But we can also allow those infrastructures to communicate between them, to allow further improvements and to learn on each other and really leverage on the new technologies, what we mentioned. So thank you very much for your attention, and now I would like to ask you, do you have any questions? So did you find interesting the presentation, and are you curious about? Okay, thanks.
We have a question here.
A very good story, thank you very well. Do you also deep dive in digital twins, that you can, every UPS has another story, and then you can say in the future with digital twin, one component has more, even further, how you call that, further earlier maintenance needs than the other one?
Absolutely. So on the UPSs, we monitor all the parameters and devices, and you can have information on each and every part of the UPS. We are actually working on doing exactly what you said, so having the predictive algorithm, so having the idea exactly what should I maintain and when. So you know that UPS has a lot of consumables such as capacitors, the fans, and so on. And then exactly with the digital twin, I can really realize which part of the UPS is maybe closer to end of life or needs to be maintained.
Every UPS has another life, and that's what I mean. Okay,
exactly. You. Thanks for the question.
When do you feel these digital twins will be available?
This is a good question. We are very close, I would say. So already, as you saw on the circuit breakers, we do have this technology. So in next years, I mean, I cannot speak about exactly the deadlines, but very soon this is something that will happen very
so it's
in the very near
development,
future.
not R&D. So it's product development, not R&D.
Yeah, exactly.
Okay. All right. Okay. Andere vragen? Het was nogal een technisch verhaal, dus ik kan me haast niet voorstellen dat het allemaal in één keer duidelijk is. Maar kennelijk toch wel. Oké, als er geen andere vragen zijn. All right, thank you very much, Aleksandar.
Thank you very much, everybody. Thanks for the attention.